Hello everybody, welcome to chapter 2.4. Today we're going to talk about the chain rule. The chain rule is used to help us find derivatives of composite functions. So that's exactly what we're going to find, and we're also going to talk about how we can use logarithmic properties to help us differentiate, and we're going to go over some important trigonometric derivatives that you should know as we move forward. To begin, let's talk about the derivative of composite functions. And the name of the game for this topic is really using the chain rule, just like our chapter is titled. And here is what the chain rule says. The chain rule says that for any function, for any composite function, for any f of g, that you take the derivative of the outside and you multiply it by the derivative of the inside. Derivative of the outside times the derivative of the inside. And what that looks like is f prime, and then we keep whatever's inside, just stays there, and then we say times g prime, times the derivative of what's inside. So let's, for example, look at something we already know how to do. We know we would use the power rule when we have something that's just like this. Y equals just x to the 7th power. We could use the power rule here to differentiate. To find y prime, we would put the power in front, 7, and we would decrease that power by 1/6. And that would be our derivative. We understand to use the power rule when we have a variable to a power. However, here's an example of when you need the chain rule. When you need to do chain instead of just power. If we have something like y equals 3x plus 1 to the 7th, this is a little bit different. We don't just have an x in there, we have more than an x. We have a whole expression, a whole function in and of itself. We have a 3x plus 1. So what we need to do is we need to treat the outside of this thing to the power of 7, just like we did before. We're going to use the power rule to help us differentiate the outside. So we're going to say that y prime is equal to, again, here's what we're doing. We're taking this stuff and we're going to use the power rule. And so we're going to say 7 in front of what's inside to the 6th. And that takes care of the outside. Now let's deal with the inside, the 3x plus 1. We say d dx of 3x plus 1. We still have to take that derivative. So we still have 7 outside, 3x plus 1 to the 6th. That didn't go anywhere. Now if we take the derivative of 3x plus 1, the 1 would become 0. And then we would get 3 times the derivative of x, 3 times 1, which is just 3. Now we can see that we have a 7 and a 3 to multiply together, so we get 21 outside 3x plus 1 to the 6th. And that is the chain rule. Let's use one more example to help us illustrate this. Another basic chain rule example. So say that we were given 3x minus 2x squared all to the 3rd power. We can see right away again the chain rule is needed here because we have something inside and we have stuff going on the outside. So let's take care of the outside stuff first. We're going to do the derivative of the outside. So when we take f prime of x, we're going to take the derivative of the outside. We're going to use the power rule. So we're going to put our 3 in front keep what's inside, keep 3x minus 2x squared. And then using the power rule, we put the 3 in front, and then we do 3 minus 1, so we'd get to the 2. And remember, the rest of chain rule says that we have to multiply also by the derivative of what's inside. So we're going to multiply by the derivative of 3x minus 2x squared. And so we get 3 outside 3x minus 2x squared. And then we take the derivative of what's in here. Taking the derivative of 3x means that we're going to have a 3, and then taking the derivative of 2x squared, well, the 2 would come in front, so we would get 4, and then we would get just x. And that's as far as you have to go. I'm not going to make you expand out that binomial and go super crazy. This is acceptable for a stopping point. And again, make sure you label f prime of x. Okay. The thing to remember or to realize about this is that chain rule is not always the thing that you do first. Sometimes you're going to need to use the other rules we've learned, like product or quotient, or even power rule, before you can use the chain rule. So here's an example of when you would need to use the product rule before chain rule. So say we're given the example, find f prime of x for f of x equals x squared times the radical 1 minus x squared. Okay. The first thing that's going to be important for us to do is to rewrite this. I hope are understanding by now that half of differentiating correctly is really just rewriting your function correctly. Rewriting your function so that it's easier for you to understand what to do. So when we rewrite, we're going to get x squared, and then we're going to say this whole thing to the power of 1/2. So 1 minus x squared to the 1/2. Now we can see that the product rule applies. We have something times something else. So we can use the product rule, which says that we take that x squared, we take that f, the first thing, the first piece, and then we multiply it times the derivative of the second piece, 1 minus x squared to the 1/2. And then we say plus, and we have just the second piece by itself, 1 minus x squared to the 1/2. And then we say times the derivative of the first piece, x squared. And we get to put this all over, oh, pardon me, I'm thinking of quotient. So forget, it's not over something, this is just what we're going to do. Okay, so when we take the derivative of 1 minus x squared to the 1/2, this is something that we are in fact going to need the chain rule for. We're not going to need it here, and we're not going to need it for anything else, but we do need it right here to take this derivative. So let's get started with that. If I were to take the derivative of this whole thing, first I'm going to take the derivative of what's going on outside. So I have something to the 1/2 power, which means that I put the 1/2 in front, and then I say 1 minus x squared to keep what's inside, and then I say to the 1/2 minus 1, or to the negative 1/2. And then I say times the derivative of what's inside here, times the derivative of 1 minus x squared. So if we keep on writing this out, we get 1/2 times 1 to the negative x squared, 1 minus x squared to the negative 1/2. And then out here, we would put our 2 in front, so we'd get negative 2, and then we would get to the 2 minus 1. So we would get times negative 2 just x, times negative 2x. That's the derivative of negative x squared. Now, what we can do further is simplify. What we can get going here is that we have a -2, let me use a different color, a -2 and a 1/2. A -2 times a 1/2 is just going to be -1. And then I also have this negative x out front, so when I rewrite this whole thing, I'm going to have a negative x in front of a 1 minus x squared to the -1/2. Now before I start taking care of negative exponents and moving everything down, let's not forget about what we began with. Right now we just found this one piece right here, and we still need to include the rest of what we started with. So remember, we still had x squared times this whole thing, and we still had plus this 1 minus x squared to the 1/2, and we still have a derivative of x squared, which is going to end up being 2x. Alright, so now when we begin to rewrite everything, what we can do is we can see that this x squared and this 2x can, in fact, this x squared and this negative x, we can multiply them together and we can get a negative x cubed. So we'll get negative x cubed outside the 1 minus x squared to the -1/2, and then we have plus 1 minus x squared to the 1/2 times 2x. Now here's what's important to see. Both terms here have a 1 minus x squared to a 1/2 power at least. And then they also both have an x out front. So what we can do is we can factor out that x, and then what we're left with, if we took out an x from here, we also need to take out a 1 minus an x squared to the -1/2. Okay. To the -1/2. And then here's what we would have. If we took out an x from right here, we would have a negative x squared. And if we took out the 1 minus x squared to the -1/2, if we took that out, then we don't need to rewrite it in here. We can just say plus. And now we took out an x, so this x isn't going to be written, it's going to be just 2 out front. But then we took this whole thing out to the -1/2. So what we have to say is still in here. What -1/2 plus what would get us positive 1/2, and that would be plus 1. A -1/2 plus 1 would get me a positive 1/2. So I have this whole thing, but now it's to the power of 1, because -1/2 plus 1 would have gotten me my original expression. And now that we have rewritten everything to our satisfaction, what we can say now is that this negative exponent out front needs to go to the bottom. It can't hang out here anymore. It's negative. So when we rewrite f prime of x, we say that we have this x on top, and we have this 2 distributed to the 1 and to the negative x squared. So what we have going on in here is a negative x squared plus 2 minus 2x squared. So what we have then is a 2 minus a negative 3x squared. And then on the bottom, like we talked about before, we have to have now the square root of 1 minus x squared. And that is our final answer. All right. The next thing we're going to talk about is when we use quotient rule first. So sometimes we'll have to use the quotient rule before the chain rule. So say that we were given f of x is equal to x over cube root of x squared plus 4, and we are asked to find f prime of x. Well, again, just like we talked about, a key thing here is to rewrite your function. And we're going to rewrite this as x over x squared plus 4 to the 1/3. You can see there's a pattern to my rewriting. Typically, if I have a radical, I'm not interested in keeping that a radical. It's hard to derive. What's easier to derive is a power, an exponent. So whenever you have a radical, it's always a good idea to rewrite that as an exponent. Now, what I can see is clearly going on is this thing divided by this thing. So I'm going to use my quotient rule. When I start writing f prime of x, I take the bottom thing, so I take my x squared plus 4 to the 1/3, and I multiply it by the derivative of the top thing, x. And then I subtract the top thing times the derivative of the bottom thing. X squared plus 4 to the 1/3, and I put that whole thing over my bottom thing squared. So my x squared plus 4 to the 1/3 squared. Okay, and as you can see here, I won't need anything special to take the derivative here, and I won't need anything special to square this. However, what I've got going on over here, derivative of x squared plus 4 to the 1/3, this one absolutely needs the chain rule. So let's take care of that first. I'm going to say chain rule, and let's just draw kind of like a dotted line. Let's take care of this guy. I know that if I was going to use the chain rule, I'd have to take care of what's on the outside of this thing first. And it looks like I have a power to the 1/3 first. So if I use the power rule there, my 1/3 comes out front. The inside does not change at all. I still have x squared plus 4. And now using the power rule, I would have to the power of 1/3 minus 1, which would be a negative 2/3. And then I multiply still by the derivative of what's inside. The derivative of x squared plus 4. I can tell you right now, a common mistake is forgetting about this second part. Don't forget to take the derivative of the inside as well. So I still have my 1/3 outside x squared plus 4 to the negative 2/3. And when I take the derivative of here, I know the derivative of 4 is just going to be 0, and the derivative of x squared is going to be 2x. And so I've got some good stuff going on here. What I'm going to need to do from this point onward is I'm going to put this back into my original derivative that I was starting. So we can say over here that we still have x squared plus 4 to the 1/3. And if we take the derivative of x, we would get just 1, so nothing else happens there. And we would say minus, and then we would say x outside of this whole thing. X times 1/3 x squared plus 4 to the negative 2/3 times 2x. And I have that all over x squared plus 4 to the 1/3 to the 2. So you can see what happens here when I have a power to another power, I multiply them. So what I actually have is x squared plus 4 to the 2/3. Now when I begin to simplify even more, what I get to say is this. I can take out this constant that is in front of my second term on top, and I can put that in front of everything. The next thing I can take out of the top is this x squared plus 4 to the 1 to the negative 2/3. And here's what's left inside when I do that. On the top, the first term didn't have a 1/3, and I took a 1/3 out of it anyway. That's okay as long as there ends up being a 1 here. So what I need to multiply by then is a 3 in front. And then I took out a negative 2/3, but I didn't have a negative 2/3 power here. And again, that's okay. I just need to make sure that I multiply by something that will get me a 1/3 power in the end. And negative 2/3 plus 1 is what will get me 1/3. So what I have then is x squared plus 4 to the 1, or just x squared plus 4. And again, that works because when I multiplied these two binomials together, I would get x squared plus 4 to the 1/3. And this is the top of my fraction. And then I get to say minus 2x squared. And here's where the 2x squared comes from. Up here, I took out this 1/3 times x squared plus 4 to the negative 2/3. I took that out. It's over here. And so the only two pieces that are left are x times 2x. X times 2x is going to get me 2x squared. And now on the bottom, let's close that bracket, I've still got my x squared plus 4 to the 2/3. That didn't go anywhere. I only took this away from the top. And now what I can do is I can distribute this 3. And so I'm left with 1/3 outside x squared plus 4 to the negative 2/3. And then on top in my fraction, I have a 3x squared plus 12 minus 2x squared all over my x squared plus 4 to the 2/3. And now what I get to do, last thing usually, is putting everything where it belongs. So what I've got going on here in the end is I've got this negative exponent that's going to need to join the denominator here. I have this 3 that's also going to need to join the denominator, and I have a 1 which won't change the top. So what I've got going on is on the top I have a 3x squared minus a 2x squared, so I get just an x squared on top, plus 12. And now my bottom needs to have the following changes. It needs to have a 3 out front, and then when I have x squared plus 4 times x squared plus 4, what I do is I add their powers. Remember, this negative 1 would become positive, so I would have 2/3 plus 2/3, which is going to get me to the 4/3. And that would be your final answer for f prime of x. Okay. Sometimes you're going to have to use the chain rule first and then other things. So this is an example of when you would need to use the chain and then the quotient rule. use the chain rule to get to your quotient rule? Here's what I mean. Say you were given y equals 3x minus 1 all over x squared plus 3, and the whole thing was to the second power. And you were asked to find y prime. Well, lucky for us, we don't really need to rewrite this one. What we get to do instead is understand that this is the chain rule. That's the first thing we need to do here, is take care of our chain rule. We clearly have something going on the outsides. We have this whole thing to the second power, right? This whole thing to the second power, which means we can apply the chain rule, apply the power rule here. We put that 2 out in front. Let's make sure we're saying y prime equals. And we keep what's inside exactly the same for now. We say 3x minus 1 over x squared plus 3. And then we change our power out here to 2 minus 1, or to the first. But that's redundant. I don't need to write that again. I can just leave this as the first part. And now I need to take the derivative of what's inside. I need to take the derivative of 3x minus 1 over x squared plus 3. Well, this one's not so bad now. What I need to do from this point onward is the quotient rule. Okay. And when I apply the quotient rule, what I'm going to get is the bottom thing, x squared plus 3, times the derivative of the top, 3x minus 1, minus the top thing, 3x minus 1, times the derivative of the bottom thing, x squared plus 3. And this whole thing is going to be over x squared plus 3 squared. As I start to simplify here, I get x squared plus 3, and the derivative of 3x minus 1 is just going to be 3. And then I have minus 3x minus 1 times the derivative of x squared plus 3. Well, the 3 would go away, and the derivative of x squared is just going to be 2x. And then I still have all over x squared plus 3 squared. Now on the top, I can distribute the 3, and I can distribute the 2x. And when I take care of that, I'm going to get a 3x squared plus 9. And over here, let's kind of do this piece by piece for a second. I would get, because what we have right now is like a bracket situation. We would have 2x times 3x, which would be 6x squared, and then I would have minus 2x. But we have this negative out front, so we're going to change the sign of everything we just said. We're going to have a negative 6x squared, and we're going to have a positive 2x. And we have this, again, all over x squared plus 3 squared. But let's not forget about where we started. This whole thing right here is just this the second piece here of the derivative of this guy. So here's the derivative of this guy, and we're still multiplying by this front piece. So we need to take this front piece, we need to bring it back down. And we still have 2 times 3x minus 1 all over x squared plus 3. We still have that times this whole thing. So then when we rewrite everything out, we get two outside 3x minus 1, and if we simplified away our pieces in here, we would get negative 3x squared plus 2x plus 9. And on the bottom, we have a x squared plus 3 to the first times an x squared plus 3 squared. We add the 2 plus the 1, and so we get the whole thing over x squared plus 3 cubed. And this would be our final answer for y prime. Okay. Here's some things you should know. I'm just going to give you some basics. Whenever I'm going to write YSK in your notes from now on, that's what it stands for. YSK stands for you should know. All right. The following derivatives are going to be very, very useful for you to have. You should know that the derivative of sine of any any little function, any little piece in there, is the same as saying cosine of the function times the derivative of the function. Tangent of some function, not just x, but something that's going on in there, is secant squared of that little function times the derivative of that little function. The derivative of secant, with a little piece in front, not just a variable, but like a little function, would be secant of that function, tangent of that function, all times the derivative of that function. The derivative of e to something is the same as saying e to that thing times the derivative of that thing. Few more. Derivative of cosine of a little function is the same as saying negative sine of that thing times the derivative of that thing. Derivative of cotangent is the same as saying negative cosecant CSC squared times the derivative of the second thing. The derivative of cosecant would be negative cosecant, so that's a CSC u cotangent u times the derivative of u. Again, where u is some function. Okay, so let's do some examples of this. We're given y sine of 2x. Well, here's the u that we got going on. So y prime, if we follow our rule up here, is the same as saying cosine of 2x times the derivative of 2x, which is just 2. So we get 2 cosine 2x as our answer. If we wanted to know the derivative of y equals e to the 3x, well, here is our u this time. So if we follow our rule, we know y prime is equal to e to the 3x times the derivative of 3x, which in this case is just 3. And then we get 3 e to the 3x as our answer. Last one. So if we have y equals cosine of 3x squared, here is a good way to rewrite this. That y equals cosine parentheses 3x squared. Okay, yeah, now this is a lot easier to see what u is. Here's u. And so when we write y prime, we say the cosine rule, which says that negative sine u times derivative of u, negative sine of 3x squared times the derivative of 3x squared. So we get negative sine 3x squared. If we do the power rule, so we put the 2 out front, we get 3 times 2, which is 6, and we get x to the first. And we always want to put our numbers or variables in front, so we're going to get negative 6x sine to the 3x, sine of 3x squared. And that would be our final answer for y prime. Okay. Some other things you should know. That the derivative of natural log is 1 over x. And the derivative of natural log when you have something more than x, right, ln of u, is the same as saying that derivative of u, the derivative of the function, all over whatever u is. And remember, u is not the variable. U is saying some function, something more than just x. So if we do some examples of this, make it more clear. If we were given y equals natural log of 2x, we can see pretty clearly that the 2x is what would qualify as a u value, right? It's not just the variable, it's something else attached to it. So we're going to use our u prime over u rule. And so if we take the derivative of 2x and we put it over 2x, say y prime equals the derivative of u over u, we get the derivative of 2x would just be 2, and we'd have 2 over 2x, which would just be, cross these guys out, 1 over x. If we had the example that y equals natural log x cubed, whoa, before we look at u or anything like that, check it out. This is a chain rule operation. We have a power on the outside, we have something going on inside, so we need to take the derivative of the outside and the inside separately. When we start to do that, we can take the 3 and we can put it out front, and we say ln of x, and then we say to the power of 3 minus 1, and 3 minus 1 is 2. And then we say times the derivative, don't forget the inside, times the derivative of ln of x. This guy doesn't change, we still have 3 times ln of x squared, but now we know that the derivative of natural log x is just 1 over x. So we say times 1 over x, we rewrite the whole thing, we get 3 times ln of x squared all over x, and that is our final answer for y prime. Okay, moving on. Last topic we'll talk about is using logarithmic properties to differentiate. And here's an example of what we could do there. We could say if f of x equals the natural log of radical x plus 1, well, you guys are pros at this by now, and you remembered me telling you that a good thing to do whenever you have a radical is to immediately rewrite. So we're going to say that we are actually finding the natural log of x plus 1 to the 1/2. Now, while we're still rewriting, what we can understand here is recall the power property of logarithms. If we have something to a power with a logarithm, remember what we get to do is we get to take that power and we get to put it in front of our log as a constant. So we get 1/2 natural log x plus 1. Now, what we've got going on, when we find f prime of x, we're actually finding f prime of x of 1/2 natural log x plus 1. So, we get to take that constant and we get to put it out front, and we're still taking the derivative of natural log x plus 1. And here's something that we get to say. Natural log x plus 1, when we take the derivative of that, what we've got going on is a little bit of a u situation, right, where we have the little function inside more than just x. Remember, we take care of that by doing u prime over u. So, we still have 1/2 out front, but now we need to do u prime over u. So we need to do times the derivative of, times the d dx of x plus 1 all over x plus 1. And guys, the derivative of x plus 1 is just 1. So we get 1 on top over x plus 1, and we get 1/2 times 1 over x plus 1, so we get 1 over 2 outside x plus 1. And that is our final answer for f prime of x. Okay, thanks for watching. We'll see you in class tomorrow.